We often look at the ground beneath our feet and think of it as just static, unchanging rock. I mean, it feels pretty permanent, right? But today, we're going to completely shift that perspective. I want you to think of the Earth not as a dead stone, but as a massive, dynamic, thermodynamic machine, a literal planetary engine. Over the next few minutes, we're going to pop the hood and look exactly at how this incredible explainer of our Earth's mechanics operates.
All right, let's dive right in. Here's a quick look at the diagnostic roadmap for our system check today, covering everything from the Earth's layers to the fiery hotspots deep within.
First up, Section 1, Earth's physical layers. Think of this as getting to know the chassis and the fluid of our machine. Okay, so to understand the rules of our Earth simulation, we have to look at two absolutely crucial layers. The lithosphere is that rigid, solid outer shell of the Earth. It includes the crust and the very top of the mantle. Basically, it's the chassis of our machine. But here's the kicker. It doesn't just sit there. It's actually floating on top of the asthenosphere. The asthenosphere is this incredibly hot, high-pressure ductile layer beneath it. It is solid rock, sure, but under such immense heat and pressure that it actually yields and flows slowly over geological time. It acts kind of like a highly viscous fluid, which is exactly what allows those rigid plates above to glide around.
And this dynamic brilliantly illustrates the engine's balance. You see, continental crust is made of lighter felsic minerals. It's older, it's thicker, and because it's so much lighter, it basically floats higher up on the mantle to form our continents. On the flip side, oceanic crust is packed with much denser mafic minerals like basalt. It's way younger, and because it's heavy and dense, it sinks lower, creating those deep basins for our ocean floors. This constant dance of density differences is literally the heartbeat driving our tectonic engine.
Moving right along to Section 2, the plate tectonics evidence. How do we actually trace the history of this massive system?
Let's look at how this builds over time. Back in 1912, a scientist named Alfred Wegener looked at a map and noticed, hey, these continents fit together like puzzle pieces, which led him to coin the Pangaea hypothesis, the idea that all land was once totally connected. But he couldn't actually prove how they moved. The real proof came later. We now know that about 210 million years ago, in the late Triassic, this massive supercontinent started breaking apart. Fast forward to the mid-Mesozoic era, and the Atlantic Ocean literally opened up via seafloor spreading, pushing the continents apart and slowly arranging the tectonic plates into the modern configuration we know today.
So what are the exact mechanisms geologists use to track these ancient movements? Well, it boils down to three main clues. First, seafloor spreading. We've found out that brand new oceanic crust is continuously being born at underwater mid-ocean ridges. Second, rock ages. When you date the ocean floor, the oldest oceanic rocks are found hugging the continental coastlines, while the youngest ones are right there at the central ridges where they just popped out. And third, this one is super cool, paleomagnetics. As lava cools at these ridges, the magnetic minerals inside it align with Earth's magnetic north. And since Earth's magnetic poles actually reverse periodically over millions of years, it leaves this symmetrical geological barcode of magnetic stripes right on the seafloor. It's absolute proof that the crust is expanding outward. Now check out how perfectly this breaks down the mechanical relationship between stress, strain, and fault types in our engine. It's like a neat set of rules. Tensional stress causes stretching, which gives us divergent boundaries and normal faults. Compressional stress, on the other hand, shortens and thickens the crust. That gives us convergent boundaries and reverse or thrust faults. And shear stress? Well, that just tears the crust right down the middle laterally, creating transform boundaries and strike-slip faults.
That brings us to Section 3. Let's look closer at divergent plate boundaries, where it's all about creation and tension. Let's walk step by step through the actual life cycle of crustal creation. Step 1. Tensional stress forcefully pulls the lithosphere apart. Step 2. Because of this intense pulling, the tectonic plates diverge and the crust physically thins out. Step 3. This thinning removes a massive amount of weight from above, allowing incredibly hot mantle rock to rise upward, which releases an immense amount of pressure. And Step 4. This sudden drop in pressure causes a crazy phenomenon called decompression melting. It generates fresh, basaltic magma that erupts, heals the rift, and cools to create brand new oceanic crust. It is literally a continuous conveyor belt of rock. To ground these abstract concepts in the real world, let's look at where our planetary engine is pulling itself apart right now. Underwater, we've got the Mid-Atlantic Ridge, a massive mountain chain slowly widening the Atlantic Ocean. Up on land, there's the East African Rift System, where continental crust is actively thinning and will eventually create a brand new ocean basin.
And right here in the US, you can look at the Basin and Range Province in Nevada and Utah, which is literally stretching out into parallel mountains and valleys thanks to intense extensional forces.
Section 4 takes us to convergent plate boundaries. If the last section was creation, this one is all about compression and destruction. Here's the crucial difference to keep in mind. Crust melting back into the mantle versus crust buckling upward. Think of it like a massive geological car crash. At subduction zones, a denser oceanic plate, like the Farallon Plate or the modern Cascadia subduction zone, takes a dive deep underneath a lighter continental plate. As it goes down, it releases water, which forces the mantle above it to melt, fueling these massive volcanic mountain chains. Conversely, at collision zones, you have two highly buoyant continental plates crashing together. Neither one wants to sink. So what happens? They smash together and buckle violently upward, forming massive, broad, non-volcanic mountain ranges. We're talking the Himalayas and the Alps here.
Section 5. Transform plate boundaries. This is where we see pure shear and tearing.
At these spots, there's no creation or destruction of crust at all, just pure shear stress. The sliding tectonic blocks just move laterally past each other. For instance, if you look at the famous San Andreas Fault in California, it's what geologists call a dextral or right lateral strike slip fault, meaning no matter which side of the fault line you're standing on, the other side looks like it's moving to your right. The Dead Sea Fault between Jordan and Israel, that one is a sinistral or left lateral motion. We see this intense shearing at the Enriquillo Plantain Garden Fault in Haiti too. The friction along these boundaries is just immense. It locks the rocky plates together until they finally violently snap, releasing massive earthquake energy.
But hold on a second. If all of this crazy action, the pulling, the crashing, the sliding, is happening at the edges of the plates, it brings up a major anomaly. What about the intense volcanic activity that happens thousands of miles away from any plate boundaries? How does our planetary engine explain that?
That perfectly sets up our final section. Section 6, mantle plumes and hotspots.
Hotspots are essentially deep thermal vents that punch right through the middle of our moving lithospheric plates. They're fueled by mantle plumes, which are these ascending columns of solid, superheated rock rising up from the very deep mantle, like a geological blowtorch. Because the hotspot stays relatively stationary while the tectonic plate above it just glides on past, it leaves a sequential track of eruptions. The Hawaiian Islands are a textbook example. Basaltic shield volcanoes continually building up from the seafloor as the Pacific plate moves over the plume. Yellowstone caldera is another classic example, but here the hotspot tracks under the thick North American plate, melting felsic rock to create massive explosive continental volcanism. If you look closely at the craters there, you can literally trace the plate's movement over the last 17 million years.
I want to wrap up this explainer with a thought to chew on. If the Earth's surface is a shifting puzzle, heat is the hand constantly rearranging the pieces. What will our planetary engine build or destroy next? Keep that question in the back of your mind. Our planet is constantly recycling itself, erasing old landscapes and forging new ones in this beautiful, sometimes violent, thermodynamic cycle. Every mountain, every ocean basin, every earthquake, it's all just a symptom of this incredible machine hard at work. Stay curious, keep looking at the world as a dynamic system, and we'll catch you in the next one.